Every time vectors are taught, math professors are obligated to point out that there's a list of algebraic properties of vector operations. These are important because they point to some of the foundations of algebra and place the entire framework of vectors inside a larger narrative of how we do algebra. If you go on to take upper division courses in mathematics, you will almost certainly run into these again. They are very useful in formal proofs and derivations, but at this level, I think the outcome for most students is just to remind you of the names of certain algebraic properties and recognize how these rules reflect the standard rules of algebra that you already have in your experiences. In the previous video, we hinted a bit at these by using your algebraic experiences to do some vector manipulations. This section formalizes all of that into a list of properties. We will go over them briefly and not get bogged down in the proofs and the details. The first two are the commutative and associative properties of addition. These should be very familiar. The third is the existence of a zero vector that functions as the additive identity. The fourth defines the additive inverse. You may not recognize these in this form, but they are a reflection of some of the basic properties of real numbers. Notice how the vector arrow above the zero vector distinguishes it from the number zero. The next two are distributive properties, but notice that one is the distributive properties of vectors over scalars, and one is the distributive property of scalars over vectors. Although they look similar, these two distributive properties are slightly different from each other because they operate on different types of objects. Then we have a property that looks like the associative property of multiplication, except it's technically slightly different because it's a product of two scalars and a vector, not the product of three scalars. The last one is the multiplicative identity property for the scalar 1. You can actually prove all of these by writing out generic vectors in component notation and using component-wise manipulations. The key fact is that once you're working with a specific component, you're just doing arithmetic with real numbers, so that the properties of real numbers apply. But we're going to leave those as exercises. If you intend to go on to take more upper division math courses, these are exercises that are important for you to understand because it will help to develop your intuition and experience for proofwriting. The important thing is not the algebraic manipulation per se, but that you understand what you're trying to accomplish with those manipulations and how you actually do it. When we introduced the idea of vectors by using arrows, we said that the magnitude of a vector is its length, but we never talked about how you would actually compute the length. Fortunately, we have the Pythagorean theorem to help us. If we draw a vector, we can form a right triangle out of it where the legs are parallel to the axes and the vector itself is the hypotenuse. The lengths of these legs correspond to the component form of the vector. Then we can calculate the length of the hypotenuse for the Pythagorean theorem. This gives us a formula for the magnitude of a vector. If we had 3 dimensions, the formula would generalize how you might expect. These formulas should remind you of the distance formula, which could also be used to find the magnitude of these vectors if you are given the coordinates of the tip and the tail. There is a special category of vectors called unit vectors. A unit vector is a vector of length 1. Unsurprisingly, the standard unit vectors happen to have length 1, but they aren't the only ones. There is a unit vector pointing in every direction, and the same is true in 3 dimensions. An important calculation is to find the unit vector that points in the same direction as some given vector. If you are given a vector v and you want to find the unit vector that points in the same direction, you need to scale the vector by the appropriate value so that it has unit length. That scaling factor turns out to be 1 over the magnitude of v. This makes intuitive sense if you think of a few examples. If you have a vector of length 3, how much do you need to shrink it by to make it have length 1? It must shrink down by 1/3, or by 1 over 3. And that's the basic idea. There's an algebraic derivation of this that comes from proving that the magnitude of k times v is equal to the absolute value of k times the magnitude of v. But that's part of one of the activities, and so it's better for you to work that one out for yourself. It's important to have a solid foundation in these basic vector manipulations because we're going to use them throughout the course.